Alright, so this section's a big section. It's again, the last few videos were on the theory behind the fundamental theorem of calculus and how integration, antiderivatives relate to area, alright, and determining area using the accumulative sum of a bunch of rectangles, or Riemann sum. Alright, so again, in the last sections, what we found was that the limit of the Riemann sum, alright, limit of those rectangular areas as they approach, again, infinity, infinite number of rectangular areas, can be found using the limit definition. And so we're going to formalize it here in this part, which the formalization of it is the fundamental theorem of calculus. Alright, the fundamental theorem of calculus is a very, very special limit that is used in a lot of applications. We only scratched the surface in this class. Alright, so the fundamental theorem of calculus, well, it has its own name and its own notation, just like the derivative was the limit of the average rates of change. We called it the f prime of x function, which was the change in my y per change in x at any moment on my function. Well, the fundamental theorem of calculus is basically the very special type of limit that is the accumulation of my function using antiderivatives. Alright, so the definite integral. The definite integral versus the indefinite. The indefinite integral was the one we found in the earlier sections of chapter 5, where we found all possible functions that have given derivatives. Alright, and so there was this indefinite part because c can be anything. This is different. This is using integration to find a numerical value. This is not a function. This is a integration that's going to solve for a value, a number, and that number has context depending on what function value, what function I'm originally given. Alright, so the definite integral is the process. It's a special limit. It's a limit of the Riemann sum for a continuous function over an interval a to b, what we talked about in the last section. Alright, note, f of x doesn't have to be positive, just continuous. No holes, gaps, or asymptotes. So it can be positive or negative, meaning it can be above the x-axis or below the x-axis, or both above and below. And we'll talk about that in more detail in a little bit. Alright, so the formal definition of the definite integral is, if my function's continuous between point A and point B, the limit of the Riemann sum exists. Alright, that limit of that sum, which was the function value times the change in the x value, right, the little rectangles that we added up, for all choices and subintervals where our n is the number of rectangles we have, right, and this is just that special limit that we have, so that limit that we found in the last section. Alright, so the definite integral is equal to the limit as n goes to infinity, right, this is the n value. If n goes to infinity, that change in x is going to 0, of the Riemann sum. Well, remember, the Riemann sum was the change in my x, that width, times each function value, alright, depending on whether I use the left, right, or any endpoint in my interval. And it is an infinite sum, right, because n is going to infinity. There's n of these values I'm adding up, right, where the change in x represents this. And that is approaching 0, right? That would be the width between each of my areas. And what it boils down to, well, if that's approaching infinity, if n is going off to infinity, right, n is shooting off to infinity, that means that fraction is shooting off to 0. This is really just the accumulation of all of my function values between a and b, right? It's the sum of all of my function values, my y values, from point A to point B. And so this is the definite integral. It's a limit. We give it its own name and its own notation. So the definite integral is what this limit's called. Alright, the notation that we use for this limit equals the following notation. Alright, it's the integral symbol, so it's elongated s. This is where the elongated s comes from the fact this is an infinite sum of my function values from A to B. Alright, A is considered the lower limit, B is the upper limit, and so it's my starting point, my stopping point of my function f of x with respect to x. That's what that limit equals, alright? So the limit is equal to, and so they're the same thing. This limit is this definite integral, alright? So they're just shorthanding it here with this, and allows us to solve it with integration. All right, just like when we did the derivative, it was the limit of the difference quotient equaled f prime of x. Well, this is the f prime of x part for my definite integral. All right, and what it solves for, what it's literally finding, is the sum, the limit of this sum. And so this is an accumulation function, meaning it finds the sum of all the function values, all the y values, from x equals a to x equals b. All right? And that has to do with area. All right, so it's an accumulation function. It accumulates all of the function values, the y values, from point A to point B. All right, that's what this definite integral is doing. And the fundamental theorem is what we're going to get to, allows us to solve this with a very special type of integration. All right, again, my note here, this does not say anything about the function being non-negative positive. It has to do with area, and we'll investigate this in a second. That's my next set of notes. All right, it has something to do with the area under the curve. It has to do with the fact that I'm accumulating all my function values. And there are two cases that come out of it, depending on if my function stays positive or if my function has positive values and negative values. All right, so we're going to look at that now. All right, how this relates to the area under the curve. All right, so we want to find the definite integral exactly without the limit. All right, we're not going to be solving limits of the definite integral in this class. And so we're going to get to the big theorem. All right, the big theorem here is the evaluation theorem for the definite integral. All right, which is called the fundamental theorem of calculus. Was a lot of times I'll shorthand that to FTC. All right, whenever you see FTC in my notes, it means fundamental theorem of calculus, FTC. All right, the fundamental theorem of calculus, the part that we're going to use, solves that limit without having to do the limit steps, all right, without having to do the algebra of the limit. All right, it allows us to solve it with a special type of integration. All right, so the fundamental theorem of calculus, if my function is continuous from a to b, if capital F of x is any antiderivative, it can be, there are infinitely many of them, it can be any of my antiderivatives. So usually we just find the general one without a constant, or with a constant 0. All right, but technically it can be any one we want. All right, so capital F of x is any antiderivative of my lowercase f of x. All right, this definite integral, which is the limit of the infinite sum of my function values from point A to point B, is found by first finding any antiderivative of this function. All right, any antiderivative of that function. And the notation that we're using means all I've done is undone the integral part. All right, so that means I've undone the derivative, I found the antiderivative, but I haven't taken care of my x value A or my x value b. And so we put it on here. Sometimes I use this sort of notation. All right, and that's proper notation to means I'm not finished yet. My next step is, once I've found the general antiderivative, now I'm actually going to use it. And this is how we use it. We take this big number here, the upper value, and plug it into our antiderivative. We take the lower value, a, plug it into our antiderivative, and then subtract those two numbers. Then we'll get, again, a number out, all right? Whatever that, again, value that comes out, it will be a number. That number, the FTC finds, the fundamental theorem of calculus, finds the exact change from A to B. All right, that's what it's finding. It's finding the difference, right, from A to B. And so this is the notation we want to see. All right, so when I go say solve this by hand, it's kind of like in an English class when you have to punctuate correctly, cite things correctly. Math is a language. All right, the language is the terminology and the notation. This is the terminology and the notation we want to see when you solve the fundamental theorem of calculus. All right, so now the area interpretation, the geometric interpretation of the definite integral and the fundamental theorem of calculus. There are two cases. The first case is the one we actually did when we kind of went over the theory. If my function's positive everywhere I'm looking at. Between point A to point B, my function is drawn above the x-axis. Right? Positive and continuous, so there's no holes, gaps, or asymptotes. If I solve the definite integral using the fundamental theorem of calculus, that's what this is. This is the definite integral solved using the fundamental theorem of calculus. If I'm positive and continuous over that interval, then it does find my area. And so the picture is what we talked about in the previous examples. All right, so this would be my function f of x, which is positive and continuous from some point A to some point B. All right, this area can be found by my integration, right? This area, the area under f of x from A to B equals the definite integral of f of x a to b. Right, when we solve that, that's what it finds. It finds that area. Right, because what this is literally doing, it's adding up every single function value between a and b. And when I add up every single function value between point A to point B, that's my area. All right, that's what it's finding my area. So if my function's positive and continuous, my definite integral, this process, found using the fundamental theorem of calculus, finds my area. All right, that's the first case. My function is completely positive everywhere. All right, the second case, if my function's continuous, but it might be positive and negative, and I'll draw an example where I'll have both positive and negative parts. All right, but first of all, it does have to be continuous, no holes, gaps, or asymptotes where I'm looking. All right, we solve using the fundamental theorem of calculus. All right, that's the process of solving this using the fundamental theorem of calculus. What this finds is the exact change in my area under my function from point A to point B. It's the difference in the area above minus the area below. All right, and so drawing the picture of that to try to understand what that is. So these are my x values. So suppose my function behaves like this. All right, so it's got some part above, so there's my A, and there's my B. All right, and so there's my accumulation part that I'm looking for. And so remember, this is my function f of x, so some of it's positive, up here would be positive, down here would be negative. And so when I find the definite integral, when I solve for a to b f of x with respect to d of x, it's not equal to area exactly. What it is, it takes the area above, which would be this area, and subtracts away this area below. All right, so it takes the area above the x-axis minus the area below the x-axis. All right, so it finds the difference, which means the answer could come out positive if there's more area above. The answer could come out negative if there's more area below. Or I could actually get an answer that's 0, which means the area above and below are exactly the same and they cancel each other out. All right, and if you kind of think about it in terms of an accumulation, remember what this is doing. It's adding up all of my y values. So all of my y values here are positive, right? So all of this would be a sum of positive y values. Then this part is below, right? Below would be my y's are negative. This would be the sum of my negative y values. All right, so I'd be adding and then subtracting, right? I'd be adding up, I'd be accumulating the positive, right, the area above, and then I'd be accumulating the negative, which is the area below. And so, again, there's a subtraction to it, which could come out positive or negative. And so those are the two different cases that we have. All right, so the next thing we're going to do is we're going to practice this solving the fundamental theorem of calculus by hand, and I'm going to look at the graphs to show you kind of what's happening. All right, so that'll be my next set of notes. So we're going to stop there.